Welcome back, students. This begins the lecture 10. Until now, we treated solvents as inert, simply transparent carriers. But reality is very different. The solvent actively interacts with the solute. These interactions modify quantum mechanical energy levels. A solvent is defined as a substance that dissolves a solute to form a homogeneous solution. Solvents interact through intermolecular forces such as dipole-dipole interactions, hydrogen bonding, London dispersion forces. We classify solvents into two categories, polar and non-polar. Polar solvents possesses permanent dipole moments. These arises from electronegativity differences between atoms. Electronegativity describes an atom's tendency to attract shared electrons. Because of permanent dipoles, polar solvents exhibit strong interaction, often including hydrogen bonding. The examples include water and ethanol, whereas non-polar solvents in contrast have symmetrical charge distributions or similar electronegativities. They are only weak dispersion forces exist. Common laboratory examples include hexane and benzene. These solvents' environments strongly influence absorption spectra. To understand solvent effects deeply, we must study hydrogen bonding. Hydrogen bonding is a strong form of dipole-dipole interaction. It occurs when hydrogen bonded to oxygen, nitrogen or fluorine interacts with the lone electron pair on another atom. Presence of oxygen hydrogen, nitrogen hydrogen and fluorine hydrogen bonds is the necessity condition. Energetically, hydrogen bonds are stronger than ordinary intermolecular forces but weaker than covalent bonds. When a solute enters a hydrogen bonding solvent, the solvent forms a molecular cage around it. This stabilizes or destabilizes molecular orbitals. As a result, energy gap shift and absorption wavelength changes. Common hydrogen bonding solvents include water, methanol, ethanol and ammonia. The key concept here is the lone pair. A lone pair is a pair of electrons not involved in bonding. These electrons act as anchors for hydrogen bonding. For examples, formaldehyde. Two lone pairs on oxygen. Water has two lone pairs on oxygen. Ammonia has one lone pair on nitrogen. Hydrochloric acid has three lone pairs on chlorine. The spatial distribution of these lone pairs determines how solvents interact with molecular orbitals. These interactions produce spectral shifts that we will analyze quantitatively in the next lecture. Today we learn limitations of single beam instruments, double beam in space design, double beam in time architecture, advantages of ratio measurements, solvent polarity effects, hydrogen bonding and spectral shift. In the next lecture, we will mathematically analyze solvent induced spectral shifts. Thank you.